I would die. I would be
All right, everybody, welcome. We have a lot of stuff to talk about today, so oh boy, where should we start? Well, let's start with the one that I'm sure you all have been thinking about the last few days, which is homework 2. Homework 2 is due tonight, so you still have a little bit of time to finish it up if you're still working on it. I'm going to say the same thing that I said to you with homework 1. After class, I'm going to go home and spend some time with my family. I will check Piazza one more time before the due date. Probably be around, I don't know, 9 or 10 o'clock, somewhere in there tonight. I'll check Piazza one last time before the due date. I will not be able to sit by Piazza all night long answering your questions. I'm sorry, but I will check it at least one more time. So if you have any last minute questions about homework 2, get them in, and I'll get back to you this evening. If anybody has any questions about homework 2 right now, I would certainly love to spend a few minutes at the beginning of class chatting about it. Yeah, what's up?
So everything except
Huh? I'm not quite sure that I follow. So you're trying to implement as on a query, is that right?
Yeah, it's like there's alias.
Alias, that's right. Yeah. Something that you have to import. Well, so it should be part of processing the columns. So if you've been able to process the select portion of the query, which tells you your projections, the aliases should be part of that. Something like that, yeah. Yeah. Column visitor get alias, yeah, sure. I mean, if you modified the visitors that I gave you, that's totally fine. Or if you made your own, I know some people were brave enough to create their own, that's fine. I don't actually think that you need to do that to get the alias out, but you certainly could. Certainly could. Yeah, I mean, you do have to get what is it? Is it a select item, I think, is what you ultimately start with when it comes to the columns. And I believe, I'd have to double check the API to be sure, but I believe one of the methods available to you is some sort of get alias kind of method. Not 100% on that. I'd have to double check the API, but if you dig down in the API, you should be able to find some way to retrieve that information out. Yes. Any other questions about homework 2? Yeah, what's up? Nope, just columns. Just columns. Yeah. Although it would be a similar thing, but yeah, just columns. Any other questions regarding homework 2 before we start in on today's topics? Yes?
Are regular expressions okay?
Regular expressions for
extracting
information from the query?
Yeah.
Here's what I have to say about that. There's definitely a lot of open-endedness to that part, right? And that's intentional. When you get to this level, I feel like, sending everybody down the same path is not as useful as letting people explore and find their own way. Now, that being said, if you're doing a lot of string parsing for part 2, you are probably making it harder than it needs to be. You should not have to do a lot of string parsing as part of part 2. So when you say regular expressions, to me, if you're a little bit might be required, yeah, for sure. But if you're parsing out the whole query yourself using string methods, contains, things like that, you're probably barking up the wrong tree. Use the parse tree. The parse tree has that information available to you. It's going to be much easier and much more consistent if you use the parse tree to extract that information than if you try to reparse the query yourself from scratch. So if you find yourself using string contains a lot or finding things in strings a lot, you're probably barking up the wrong tree on that one. A little bit is not a huge deal, but a lot of it would be a red flag for sure. Any other questions about homework 2? Yeah, what's up?
So the keywords and or and not included in the write-up. They fall under the umbrella of where?
So and or and not. I don't think I gave you any tests with compound conditions, right? So just singular conditions are all that's expected on this particular assignment. Yeah, our version of SQL is definitely a much narrower scope than official SQL. I mean, the SQL spec is kind of large, so I just kind of had to pick and choose a subset. Yep. Any other questions? Any other questions about homework 2? All right, so yeah, what's up? I believe that's all on the rubric. I mean, I can pull up the rubric and take a peek real quick and see. That's homework 3, which we're going to talk about a little bit later, but homework 2, query, aggregates 5 points, as 5 points. And then for the relational, here's your aggregate for just the relational objects. Yep. Any other questions? Happy to answer any questions you got about homework 2 before we move on. Yeah, what's up? Oh, do they? Probably because I added unit tests on there. If they add up to 105, then I'll grade it out of 105. That's an oops, but an easily correctable oops. So if they add up to 100, then 105, they add up to 105. We'll make it work. Yeah.
Well, but it says aggregate is 15 points, but it's only 5 and 5.
Oh, is it a... So I either screwed up my math or I screwed up my math. Is that what we're... That's what it sounds like to me. I mean, yeah, you're right, it does. It says 5 and 5. So that was probably intended to be 10. But you know, I am in favor of grading it whatever way benefits you the most. You should not have to suffer for my arithmetic mistake. So if you feel as though I approach your homework 2 grading unfairly due to this mystery 5 points, let me know and we'll work out a solution. That's not a problem. Sorry about that. Anything else I can address? Anything at all? All right, cool. So homework 3 is on the list of topics to talk about today, but actually before we get to homework 3, I do want to finish up the topic from last week. We ran out of time. We didn't quite get finished with this. This won't take very long. This will take 15 or 20 minutes, and it is an important topic. So I do want to spend some time talking to you about query tree optimization. This is sort of the grand finale of our optimization series, the optimization unit that we've been talking about for the last few weeks. And so we talked about some rules for forming heuristics, some things that we can do to query trees, but what we didn't get to, what we ran out of time last class to talk about was what the actual things are that we're going to try to apply to our query tree to optimize it. Now remember, a heuristic is not the same as an optimization, right? What's the difference between saying that I'm optimizing the tree or I'm applying a heuristic to the tree? What's the difference? What's the difference? It's a subtle distinction, but an important one. Yeah.
Heuristic is a series of actions you expect to lead to some sort of optimization, but is just from common sense, perhaps, as compared to optimizing, which is actually guaranteed.
If I say I'm optimizing the query tree, that comes with a much bigger implication. When I say I'm optimizing the query tree, that implies to me that when I am done, I have found the best possible query tree for this particular query, period, end of story, right? That's what optimization implies. A heuristic implies that, you know, I'm gonna try to do some things to make the query tree better. Is it gonna be the best possible query tree for this particular query? Maybe not, but I'm expecting it to be better than what I started with. Why do we make that concession? Why do I strive for a simple heuristic instead of actually finding the best possible query tree? Could I find the best possible query tree if I wanted to? I could, right? What would that involve? Yeah.
From using the query tree until you find the best
Trying every single one. Trying every single possible combination until I find the one that's the best. That sounds like it would take a lot of time to me. Sounds time consuming. And we're trying to speed things up in general. So we're making a concession here. We're saying, I'm not going to spend the time to try to find the optimal query tree. I'm going to apply some rules that I believe should help improve the performance of this tree. Will it be the best? Maybe not, but it should help improve the performance of this tree. So let's take a look at those rules and we'll apply it to an example. These are meant to be followed in order, right? So the order of these rules matters. So the first rule that we see in our optimization heuristic is to break up conjunctive selects. So what that means is if I have a select operation and it's a compound select operation, it's got a lot of ands and ors, usually ands, we're going to break them up. We're going to split those up into individual select operations. And the whole reason for that is so that I can move those operations up and down the tree to where I need them to go. And we can do this, again, just to refresh your memory, because of the rules that we discussed at the very end of class last Wednesday. The rules that we described allow us to use this rule. The next thing that I'm going to do after I break up my conjunctive selects is to try and move the selects as far down the tree as possible. So let's think about this just from a common sense perspective. How does this help speed things up? Where does the improvement come from doing this? I'm going to take my select statements, the pieces of my where clause, and force them as far down the tree as possible. How does that help us? I'm reducing the size of the problem as soon as I can, right? As soon as I possibly can. There might be reasons why I cannot push them all the way to the bottom. If I have dependencies on other parts of the query tree, I'll only be able to push them so far down, but I'm going to try to push them as far down the tree as I possibly can so that they are performed as soon as possible. And then any other operations that are performed afterwards should see an improvement as a result because I've effectively reduced the size of my data set. Okay? Then, when performing operations on multiple tables, so if I'm performing an operation on multiple tables, that means I'm using what? Join. So if I have a query that involves a join, a query that requires multiple tables, any relations that have select restrictions applied to them, I'm going to move as far down the tree as possible. As far down the tree as possible. The reasoning for that is actually the same as the reasoning that we talked about before, right? I want to get the smallest tables, the smallest data sets, and perform those joins first. We actually talked about join performance last Wednesday. I want to use, eliminate as much data as possible. So I'm going to start with the smallest tables and then feed in the larger and larger ones as I go up the tree. This next one seems obvious, and actually a lot of students struggle with why this is even a rule. This kind of goes back to that trade-off, that distinction that we've talked about a few times before now, the theoretical side versus the practical side of things. We are squarely in the theoretical side kind of at the moment, and so when I say combine Cartesian products with selects when possible, in practice, right, that's almost always going to be possible. In fact, in practice, I'm rarely going to see a Cartesian product at all. I'm just going to see a join. A Cartesian product plus a select is a join. So this rule for a lot of people seems unnecessary. Like, of course, I'm just going to use joins. But remember, we're talking about this from a theoretical perspective where our query trees technically can contain Cartesian products, as rare as it might be. And we do want to combine those to form joins when possible to do so. Yes?
I was just wondering, does SQL actually have a Cartesian product?
Does it actually have a Cartesian product operator? I'm not sure about the answer to that, actually. It wouldn't surprise me if it did. Even if it didn't, most SQL languages do allow you to do things like write for loops, so you could, make your own should you really, really want to. Cartesian product SQL. Let's see. Cartesian product tips. Oh, cool. Here we go. Cartesian or cross joins. There we go. Yep. It's a thing. Where's the actual query? Doesn't actually say cross join, just says from table 1, table 2, table 3. So to me, it looks like a join without a where clause, which kind of makes sense when you think about it. A join without a where clause is a Cartesian product. A Cartesian product with a where clause is, or a Cartesian product with a select statement is a join. So yeah, it looks like you can. Pretty, excuse me, pretty rare to see that in practice though, as I've mentioned. This is still part of the rules though, combining Cartesian products with selects when possible, and hopefully you can see how it would help improve the performance. If I'm performing a Cartesian product, that's every single possible combination. If I'm performing a join, that's only the combinations that satisfy the join condition. So that data set is going to be smaller, and smaller data sets is what we're after. Last but certainly not least, the last rule of the heuristic says move project operations as far down the tree as possible. Now this is similar to what we saw here, to move selects as far down the tree as possible. The fact that this is last, though, kind of tells you something about projects versus selects in terms of their effect on performance. Which one's going to have a larger effect on performance? Select operations or project operations? Select operations for sure. Project operations do make my data set smaller, and I should try to get them done as soon as possible. But reducing the number of rows is going to have a much bigger effect on my performance than reducing the number of columns, because many operations that we perform are row-based. For example, joins are row-based, right? So trying to reduce the number of rows is going to be more efficient for us in the long run than reducing the number of columns, even though reducing the number of columns still does help. Let's take a look at an example of how we can apply this to a query tree. Here is our starting point. This is a query, and actually the first thing we could do is talk about what query this represents, right? You can already see there's a few little strange things about this query, perhaps. The fact that it does, in fact, use Cartesian products as part of the query, potentially being one of them. But let's talk about this from a SQL perspective real quick. What SQL query is, that's too small maybe. What SQL query is this tree representing to us? And so typically I'm going to start at the bottom and work my way up to the top, and you can see that I've got how many tables? 3 tables. So I've got a 3-table join. And then actually it's not specified as a join because I've got these Cartesian products here. And kind of a sneak preview, right? You can see this very large compound. What do I have? 4 chunks. I've got 4 chunks as part of my select statement. Some of those are probably going to end up being combined with these Cartesian products down here once we get to that step of the heuristic. Okay? But we need to start from step 1. Step 1 says to do what? What is step 1? Step 1 is break up conjunctive selects. And we have one. We were just looking at it. I've got a select with 4 pieces. So step 1 says break those up. Those don't need to all be in one select operation. I can break those up into 4 select operations, and that's going to allow me to move them around the tree. Okay? So if I take a look at what the tree looks like after breaking it up, actually step 2 then, that's actually the result of step 2, says move selects as far down the tree as possible. So if I look at the pieces of my select statement here, right? The first one, pname equals Aquarius. So pname is short for project name. And so I'm going to want to take this particular chunk and move it as close to the project table as I possibly can. I want to move that as close to the project table as I possibly can. This one over here, B date, birth date, is greater than whatever that date is, right? That is part of the employee table. So I'm going to want to take this piece of my conjunctive and move it as close to the employee table as I possibly can. I want to do those as early on in the tree as I possibly can to reduce my data set. These, the 2 that are remaining, cannot be pushed very far down the tree because these 2 are going to represent our join conditions in this particular case. So project number from the from the works on table, and P number from the project table. Employee social security number from the works on table, and social security number from the employee table. So those have to happen after the Cartesian products. Those have to happen after the Cartesian products, because otherwise those columns won't be available for me to perform the select. So after the first two rules, breaking up conjunctive selects and using commutativity to push them down the tree, I might end up with something like this. You can see the birth date and the project name were pushed very far down the tree, but the other ones couldn't go down too far because they require the use of these Cartesian products in order to be effective. Everybody with me so far? Any questions about, we did the first two steps, breaking up the selects, pushing them down the tree? So then the next step of our heuristic says, when performing operations on multiple tables, I'm going to move the relations with select restrictions as far down the tree as possible. So if I'm looking at this, I've got three tables. Two of my three tables have select restrictions on them. The employee table has a select applied to it. The project table has a selection applied to it as well. I want those to be as far down the tree as possible. And so employee is already as far down the tree as it possibly can, but projection is not. And actually, we can take a look at this from a more nuanced perspective, right? Of the select conditions that I see here, birth date greater than such and such, and P name equals Aquarius, which one is going to be more selective? Which one do I expect to be more selective? P name equals Aquarius. Why? It's specific. Which part of the select is telling you that it's more specific? The equals sign, right? The equal sign is going to generally be more selective than a greater than sign. A greater than sign I would expect to match more values than an equal sign would. In most cases, maybe not all cases, but in most cases, that's what I would expect. So in other words, this selection is more selective than this one, which means I would rather do this one first. It's more specific. It's going to shrink my data set more than this one is potentially. So I'd rather do this one first, which means I might end up swapping the places of those two. In fact, that's going to be the result of applying step 3. Notice the project table got moved down to the bottom. I want to perform that first. I want to perform that as soon as possible. This join should now be more efficient because it's operating on a smaller tree. On a smaller table than it was in our original configuration. That's the plan anyway. So it's not necessarily just whether a select condition exists, but also what's the selectivity, what's the expected selectivity of that select operation that matters when deciding what order the table should appear in the tree. Are there any questions about that? That is another kind of tricky one that can trip people up sometimes. So then the next step is to combine select statements with Cartesian products when possible, and that is in fact possible. In this case, this selection here and this selection here can be combined with the respective Cartesian products to form joins. And so that's a pretty straightforward step. You can see they're now combined to form joins. Everything else has remained the same. Our tree is looking a little bit nicer now. And then the last step is to push projections down the tree as far as possible. This one is a little bit less obvious to think about. I have one projection up here at the top, last name. So by the end of this query, all I want to end up with is last name. Think about what that means for us farther down the tree, though. If I'm not using it as part of a selection, or I'm not using it as part of a join condition, I can project it off the tree right away. Correct? So if I look at project, the project table, all I really need from this project table are the P name column and the P number column. That's it. That's all I need from this table, and I should run that projection right away. When I'm finished with this selection, right, I'll probably even project off the P name column because I don't need it anymore after that point. It's not necessary. I've finished using it. I've satisfied the select condition, so I'll project that column off. I'm done. I'm done with that now. Same for all of the other tables. The works on table, what column do I really need? All I really need is the project number. That's it. Actually, I'm sorry, the social security number column as well. So 2 columns, project number and social security number. What do I need from employee? I need social security number, birth date, and last name. But like before, once I perform this selection, I can project off the birth date column. I don't need that anymore, so I can get rid of it. Once I perform the join, I can get rid of the social security column. So the effect that this ends up having is taking this one projection on last name and making lots and lots and lots of projections farther on down the tree so that it looks something like this. It looks a little bit more complicated than what we had before, but remember, we're doing this for the sake of performance. So again, after the projection, it kind of skips the first projection, waits for the selection. Do this selection, then project off everything except for project number, because that's the only column that I need to satisfy the join. Do the selection, then project everything except for social security number and last name, because I need one for the join and one for my result set. So I'm just going to project off everything as soon as I possibly can. Notice too that this original projection that we had at the top of the tree doesn't actually change. That's still the end result that I want, right? But I can project off a lot of other stuff earlier on in the tree. So this is our quote-unquote optimized, but perhaps not really optimized tree. This could be the optimal solution. That's certainly possible, but the heuristic does not guarantee that it is the optimal solution. So I might get the optimal solution just by chance, but it does not guarantee that I'll actually end up with an optimal solution. What we can say is that the performance of this tree is more efficient than the performance of this one that we started with. Okay? So think about how that applies to us, especially in the terms of our homework assignment. I'm not going to ask you to code query tree optimization, but I did ask you to code sort of the query tree processing for this past assignment. I asked you to think about order of operations and from a naive perspective, right? Think about what you did. You probably processed the from clause first to get your tables, did all your joins. Then you would process the where clause next, and then you would process the select clause after that. That's actually exactly how this tree is set up, right? From clause first, do all the joins, then do the where clause, then do projections. That's exactly how this tree is set up. So if we think about things from a order of operations perspective, I'm going to end up with trees like this that are perfectly functional, but perhaps could be improved, could be made better. And so by applying this heuristic, what you'll notice now is that order of operations is actually a lot less clear. Saying that I'm going to do the from clause and then the where clause and then the select clause, well, that's actually not the case. I've got, projection, selection, and joins sprinkled all throughout the tree to help me get the best performance. So it's not as cut and dry to saying which clause happens first. All right. Any final questions about this before we switch gears and talk about homework 3? Homework assignment number 3. Cool. All right, let's chat about homework 3 then. Should come as no surprise to you that homework 3 is related to B+ trees. I believe I talked to you about that a little bit ago. And so the write-up is already posted, and so we can cover some of the logistical stuff first and then take a look at the code and see what I'm expecting you to do for this particular assignment. And then also we'll do what we did last time and talk about unit tests for a bit. So just like before, I'm going to ask you to write a couple of unit tests and submit them by noon on Wednesday. So in a couple of days from now, I want you to write some unit tests. We're going to talk about unit tests later today. I'll show you some examples, and we might even write some in class potentially. We'll talk about that a little bit later on today. I want those by noon on Wednesday so that I can package those up for you and send them back to use them as you work on this assignment. The assignment itself is not due until the end of the month, so you've got a lot of time on this, and that's for a couple reasons. One reason is we've got an exam coming up. Perhaps I should have mentioned this at the beginning of class. We got an exam coming up in 2 weeks, I believe, 2 weeks from today. The exam will be right here. We'll have a review session before the exam, so don't worry about that. But yeah, the exam is coming up. So that's one reason why you got a lot of time. Another reason why you got a lot of time is because this is actually, like the last assignment, it's a pretty significant assignment. And I would very, 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 very much encourage you to please consider starting this as soon as you are able to do so. I know fall break's coming up. I get it. I'm looking forward to taking a couple days off, and you definitely should take a break. You all have earned it, but please, please, please consider getting started on this as soon as you are able to do so. It's not an easy assignment. I'm fully aware of that fact. Another reason, just to kind of dangle the carrot for you, to consider working on this sooner rather than later is that B+ trees are going to be on the exam that's coming up in 2 weeks. So working on this assignment you can think of as actually being a way to study for that part of the exam, as another reason to consider trying to get started on this sooner rather than later. So yeah, the code is already available to you. I'll go through the starter code in just a bit. But I want you to implement B+ trees as we have discussed them in this class. So we've spent a lot of time last week talking about B+ trees and going through examples in class. We can even go through more examples today. If you guys want to talk about more B+ trees examples, I'm happy to do that. But now it's your time to actually implement them, to make this happen. Okay, so if I switch over and take a look at the code real quick that I have given to you for this assignment. The only file that you are required to modify is this one, B+ tree. This is the only file that you're required to modify as part of this assignment. You can see that I've given you a constructor. I've given you 3 methods: search, insert, and delete. Those are the 3 operations that we talked about performing on a B+ tree. That's it. You just got to make those methods, right? 4 methods. Actually though, I'm hoping that you'll write more than 4 methods. So one tip from me to you, please, please, please write more than 4 methods. Please, I'm begging you, write more than 4 methods. Please do not try to cram all of the code into these 3 methods. Can you do it? Yeah, I've seen it done, right? I wish that I hadn't, but I have, right? Please write more methods. Yes? That is correct. I stopped just short of asking you to integrate it with the database. I feel a little bit bad about that, but the reason why is because, just speaking from past experience, if I asked you to integrate it with the database, you all would be very mad at me for the level of work that I ask you to do. It's too much. It's not fair to you to ask that. If that's something you're interested in, and I've had people take me up on this, I would love to chat with you about how to properly integrate this. In fact, the write-up mentions this and also mentions that it's optional, that you don't have to do it. But I would love to chat with you about how to actually integrate this with the database. Is doable. People have done it. It's really cool when you get it working. Not officially required. This will definitely keep your hands full for the next few weeks. I promise you it will. So I have provided you some other classes, and these other classes are very simple. They're very straightforward. So I'll run through them real quickly. Actually, let me start with the node classes. So this is a very simple interface that is applied by both inner node and leaf. Oh, whoops, sorry. Whoops, huh? Okay, my bad. You have to do some other methods too. My bad. I forgot about this part. These are getters, and these are getters though, so these classes are not going to be terribly difficult when it comes to writing code for your inner node and for your leaf node. Sorry about that, guys. I totally spaced it. My bad. So you do have to implement these simple methods. These should not be very complex, should not be very complicated. However, one more tip for you all that's going to sound a lot like the tip that I just said a few minutes ago. You can put more methods in here too, right? That's okay. That's all right. That might lead to some good, efficient designs, and that's what I'm trying to encourage you to do. So, put more methods in these if you want to. You do need to have these implemented at a bare minimum, mostly for testing purposes, but they will also be useful to you as you implement the tree. So obviously, inner node and leaf node classes are for the respective nodes in the tree that we talked about. This entry deserves a little bit of explanation. This one is completed for you. You do not have to add anything to this one. This is the actual key value pairs for the index. This is what's being stored in the tree. So when I say insert something, what am I inserting? I'm inserting an entry, right? I'm inserting an entry into the tree. when I say find something, what am I searching for? I'm searching for an entry. That's what I'm searching for in the tree. So this is basically just the data structure to encapsulate the key value pairs that are being stored in the tree. In this case, F is going to be some value from a column from a table, right? And this is going to be the page number where I can find that field in the table. Okay? Any questions for me so far? Yeah, what's up? We assume that, yes, actually that's a good question. For this particular implementation, we are assuming that we're dealing with unique values in the column. That is correct. The implementation actually doesn't change that much if we're assuming that duplicates can exist, but for this implementation, just to keep things straightforward, we're assuming unique values in the column. Good question. I did try to keep this as close to the examples that we've done on the board as possible. So if if you've gone through the examples on the board that we did in class, you understand what's going on. This tree is meant to mimic that as closely as possible. And actually, to reinforce that idea, if you look at B plus tree test, so I do have some simple unit tests here for you, but actually this complex insert is literally the example that we did on the board in class. This is that example, right? And so let me give you another tip on this one, especially when you're dealing with things like trying to find mistakes, because let's be real, things are going to happen. You're going to run into errors. You're going to make mistakes. You're going to, curse at your computer a few times. How do you deal with that? Be smart about it, right? Be smart about it. If I write the insert method and then I try to run this test to see if it's going to pass, it's not going to pass the first time. Like, I'm just being real with you guys, right? It's not going to pass the first time. So what do? Start with the first number. Set a breakpoint on this one, right? Set a breakpoint here. Debug the test. Watch the first insertion happen. Make sure that the nodes are being set up properly. Once you're satisfied that that is working, move on to the next one, right? Move on to the next number. Watch that insertion happen. You can actually sketch out the tree after every insertion, right? We did that in class. You can sketch out this B plus tree after every single insertion. So walk through this one line at a time, insert a number, double check the tree, make sure the tree structure is what you think it is. Insert another number, double check the tree, make sure the tree structure is what you think it should be, right? Keep repeating that process until eventually you'll notice that the structure's a little off here. It didn't split that node, or it didn't pass the search key up to its parent, or whatever the case may be, right? And then you know where to go look in your code to try and figure out where the problem is. Okay? So you can see here that I do pass in the degrees upon construction. One thing that you should also keep in mind when working on this assignment, while the tests that I provided to you here work with degrees of 3 and 2, which match the examples that we've done in class, I actually expect your implementation to work for any degrees, not just degrees of 3 and 2. In fact, if we have time today, I would love to go through an example of B plus tree that doesn't use these degrees, right? Since we've only seen degrees of 3 and 2 so far, it'd be nice to go through an example that uses a different set of degrees to see how that affects the structure of the tree. And so I've given you some simple tests here, and actually you'll notice that for these tests, they're quite a bit longer than the tests that I've given to you for previous assignments, and that is, intentional. In order to test these properly and actually to verify the output properly, it does require a bit more work. So you can see that the way that I have these tests set up is I insert a bunch of values, and then I start at the roots. I grab the root node and I just start traversing the tree one layer at a time and verifying that each layer in the tree is what I expect it to be, right? So it does take a little bit more work. I have to grab the child nodes. This is a common line where I see an error because I'm clearly expecting this to be an inner node, but if for some reason you have it as a leaf node, that's going to cause problems, right? So I see that type mismatch happen sometimes when running these tests. Just taking a look at how I'm checking these, grabbing each node and then checking each entry one at a time. I think in order for you to write your 2 unit tests that I'm requiring for you on Wednesday, you're going to have to take some time and actually look at this unit test, make sure you understand what it's doing, and then I absolutely 100% am totally okay with you sort of mimicking the style of this unit test. Don't feel like you need to start your tests 100% from scratch, you know, kind of use this same setup where I'm gonna, at the top, I'm gonna perform the operations that I want to test, and then I'll grab the root and just check every single layer of the tree to make sure the structure of the tree matches what I expect it to be after I perform those operations. It might require you to sketch the tree out on a sheet of paper, right, to make sure you understand what the structure is going to be. That's good practice. That's good practice for you. So please do that. Now, the methods that I provided to you, I have an insertion test, I have a search test, and then I have one test that tries to test for higher degrees, so 4 and 3. I believe I have a deletion test down here as well. But these tests, I think, are actually maybe even a little bit too broad, perhaps, right? Remember that when we talked about, especially insertion and deletion, there were different cases that I had to take depending on how the insertion and deletion progressed. And so really, I think better tests, and this is something where we can kind of have a little bit of a brainstorming session to give you some ideas on what tests you could write. I think better tests would focus on those specific cases. I'm going to write a test that forces a node to split after I do an insertion and then make sure the structure works, right? So what I would like to do right now is a little exercise with you all is give you a few minutes to think about what parts of the behavior of this code would be good to test. And I want you to break it into 3 categories, right? We've got 3 basic methods that we want to, actually I don't want to clip any of this. I've got search, I've got insert, and I've got delete. And so I'd like for you to take a few moments and talk to your neighbors about this, and for each of these 3 categories, right, recall the algorithm that we went through in class. Think about which pieces of that algorithm would be good to write tests for. We'll talk about what you came up with together as a group in 5 or 10 minutes, and then hopefully when you walk out the door today, you'll have a list of stuff that you can decide to test, and you'll just have to pick a couple things off that list, write some tests for them, and submit them for Wednesday. So I'm going to shut up, give you a few minutes. I'll be around if you have any questions. Think about what kinds of tests would fall under each of these 3 categories. We'll discuss in just a little bit. Okay? Actually, some reasons could be as well, right? I mean, I certainly wouldn't mind having some tests on streams, but I think actually, the way the fields are set up, you won't have to care which ones are because the field has comparison operators. You don't. You don't. I mean, once you. Remember that I'm in a column, and columns have data types. So data type was column is the keys. So they'll either all be keys or all be yeah. I mean, I could have 2 separate tests. One to test three fields work on the tree. Or just Okay, let's have a chat about these. So I want to know which cases should be tested for each of the three operations that we are working with on this particular assignment. We're going to start with search, which I feel like is probably the simplest of the three. Not as much going on. So what are the possible things that could happen? If I run a search, right, I'm searching for a value, what are the possible things that could happen that I need to accommodate for? That it exists, all right. So value, I'm sorry, it's actually the key exists, right? I'll just say exists. And then there's the opposite one too, right? Doesn't exist. Any others? It might seem like we covered all the bases with those two, right? But I think there's maybe one other potential edge case that could be worth thinking about. Think about edge cases with the tree in general. So this will matter a lot, especially when we get to insertion and deletion. These edge cases will be perhaps more worthy of thinking about. But Sometimes my tree is only going to be comprised of one type of node. What am I talking about? When it's just the root, it's only going to be what kind of node? A leaf node, right? So can I still effectively search when it's just the root? That's sort of an edge case, right? When it's just the root, can I still effectively search and find values that I'm looking for? So one other thing that we could consider here as well, although I think this one's maybe not as tricky as you might think it is. In our implementation, we have two different kinds of fields. I have ints and I have strings. All of the tests that I've given you so far use ints, but we should also be able to accommodate searching for strings as well, right? I think that's probably not as tricky as you might think at first. But theoretically, our implementation should be accommodating of both strings and ints. Not at the same time, right? I'm either going to have a tree that works with strings or a tree that works with ints. I'm not going to have a tree that works with both necessarily. But I should be able to have trees that work with any of the data types that we can support. Any other ones that you guys thought of worthy of consideration? I think this is good for this one. The other ones will be a little bit more, there'll be a little bit more stuff to talk about. So let's move on to insertion. So what are the things that are worth considering testing for insertion? Yes. Whether you need to split. Or, I mean, we can think of this in a couple of different ways, right? So the simplest case is when I don't have a split. There's no split, right? That's the simplest case. And then we could also argue that there's a case when I do need to split, but I think actually when I do need to split, there's sort of sub-cases within that we need to consider as well. So what are the things that we need to pay attention for when I am splitting nodes? What do we need to consider? So let's say I have to split a node. What happens after that? I've split the nodes, and then what do I do after I split the nodes? I update the search keys, so I pass values up the tree, right? Am I done after that? Maybe, but maybe not. What might happen after that? I might have to split a parent, right? So I can say split leaf, but not parent, not me, right? Or I could say split leaf and I have to split a leaf node and I have to split a parent node, right? There's actually one more case to consider as well in this vein. So if I take this to the extreme, what might happen? Split the root, right? Split the root. And that's the root. What is effectively happening? I'm making a new level of my tree at that point, right? All four of these cases should be tested independently of one another, ideally, right? Ideally, they should be tested independently of one another. So I can write a simple case to check to see if it's a simple insert that doesn't require a split, one that checks to see if I can split the leaf node but not the parent node, one that splits all the way up to the root, etc., etc., etc. Should have simple cases for all of those. And then there's some other cases that we should think about as well that kind of call back to the search cases that we talked about. Edge cases, especially at the beginning of the tree. What happens if I do my first few insertions, right? If I'm inserting and there's only the root. That's a special case because I need to make sure that the root is the proper node type. Only the root. So there might be some unit test case potential there as well. Any questions about that? Any questions? Anything that you think I forgot? Yeah.
To clarify, we don't allow duplicates in these trees, or?
We don't. So we're assuming that all the values are unique. And as an extension of that, If I insert a value and it's already in the tree because I'm assuming they're unique, what do? Nothing. And so that could actually be a case as well, right? Insert a duplicate. That would be a pretty simple test to write. Insert something that's already in the tree and nothing should change. Nothing should happen. Good. Anything else that you think we should be considering here that we haven't gotten to yet? Anything else? Yeah.
The simple case could be split into two, probably, where you have to update the search key when you don't have to update the search key.
When you update the search key and when you don't have to update the search. Oh, so no split. I'm sorry, say that for me one more time. Oh, it's possible to not split a node but still have to update the search key? Is that what you're getting at?
Right.
When does that happen? I'm glad you thought about that.
When you insert like a value that's greater than, oh wait, like all the way to the, I don't remember now.
It's tricky, right? Let's think about that for a second. The search key represents what as part of my tree?
The like greatest possible value.
The largest value that's in the subtree to the left, right? So the only time when that search key, if I try to insert a value that's bigger than that, it's going to send me to the tree on the right. So I'll never actually have to update the search key that way. I only have to update the search key if there is a split, right? Only have to update the search keys if there is a split. Worst case scenario, I could insert the search key itself, but that still wouldn't require me to update the search key at that point. It's already there. Yep. Anything else that we should consider? I'm glad you're thinking about this stuff, though, right? That's the kind of stuff that I want to talk to you about. All right. Let's talk about deletion then. There's probably a faster way for me to do this, isn't there? Okay. So what areas do we need to focus on when it comes to deletion? Yeah.
If it doesn't exist.
If it doesn't exist, all right. Not in tree. What should happen if I try to delete an item that's not in the tree? There are two answers that I would potentially accept. One answer is nothing, right? You could argue that you should throw an error. That could be another answer that I would consider. Which one should we do? I don't know. You tell me. You tell me what you think. Write a test, and if you feel strongly about it, write a test and tell me what you think we should do. What are some other things that we should pay attention to with deletion? All right, so yeah, let's get into the different cases that can exist. So merging is definitely one. What other cases exist with deletion that we need to pay attention to? Yeah.
Rebalancing.
Rebalancing or
Value borrowing.
Borrowing, yeah, or I called that push through, I believe, in class. If we're thinking about the same thing, rebalancing, borrowing is something different, actually, right? It depends on how it applies. The difference between these two is what? When I borrow, who am I borrowing from? A sibling. I'm borrowing from a sibling, right? Borrowing from a sibling. And actually, even borrowing could be broken down into two subcategories. At least two subcategories. I should try to borrow from the left sibling first if I can, and then also the right sibling. So that's actually two separate cases. Could write a case that borrows from the left, write a case that borrows from the right. When you say rebalancing, to me, that implies the push through. In fact, I might even write down push through seconds. What's going through? What are you doing? All right. What does push through happen? What is that technique? What nodes is that operating on? Inner nodes. So when do inner nodes enter a crisis? Or I guess another way of thinking about it is merging happens if a leaf node can't fulfill its obligation, right? This push through might happen if an inner node can't fulfill its half full obligation, right? Might happen if an inner node is at risk of being removed from the tree. So inner nodes don't merge. They try to borrow from their neighbors first, and then if that doesn't work, there's actually another case. When push through fails, what happens? I'm sorry? Inner nodes don't merge, actually. If the push through fails, then at that point we're removing a whole level of the tree. We're collapsing a level, right? I missed a letter there. Collapse a level. We also missed kind of the simple case, right? Where I can just delete a value and I don't have to do anything. That's what we're hoping for. That's the easy case. But there's a lot of more complicated cases to pay attention to here. And I think it's actually very important to test for these things because these are the complicated pieces of code to write as well. So we want to have some indication if we're doing these things correctly. I know these can be scary. I know that this is sort of the hardest part of the B+ tree implementation, but please consider tackling these challenges on the unit tests because it will make your life easier when you go to actually implement these things. Is there anything else that I'm missing? Collapse a level, merging, borrowing, push through, simple deletion. I think we've covered most. I guess we could talk about root deletion as well. If all I have is the root, right? Could talk about that as well, perhaps. And then for all of these, it should be worth considering, right? Different degrees. Strings and ints should both work for insertion and deletion as well. So that kind of is an all-encompassing idea for all three of these categories. Have to be able to handle different degrees as well. Any that you thought of that? Yeah, what's up?
I actually had a question.
Yeah.
The tree itself will only be ints or strings, it won't be both.
It won't be both, not at the same time. Yeah, it'll either be ints or strings. It's simpler than you think it is because if you treat them as fields, I believe the field interface has a comparison as part of it. So you don't even need to cast it to int or string. Just call the comparison on the field and it should work out whether it's an int or a string. So testing ints and strings is pretty low priority in my opinion, especially when we have more complex things to think about, like merging and borrowing and so on and so forth that are a bit more conceptually complex than strings versus ints. Yep. Anything else you can think of? So we got about 15 minutes left, and then what I would like to do at that time, and if anybody has any other questions or would like to discuss anything else, I'm open to the suggestions as well. But what I would like to do at that time is do a B+ tree example with some different degrees that aren't the same degrees that we've been using for every problem, just so you can kind of get a feel for what those trees might look like and how that affects the structure of our B+ tree. So that's how I'd like to use the remainder of our time. So I'm going to pull up the slides from the other day, if I can find them here. B tree. I actually have a practice problem already in mind for this. Oops. All right, cool. So we actually did this example already with these values, right? I want to repeat this example. I hope you already have this in your notes from when we did it before. I want to repeat this example, but with different degrees. I want the degree of the inner nodes to be 4 and the degree of the leaf nodes to be 3. So I've just increased them both by 1. What effect is that going to have on our tree, though? Let's talk about that real quick before you get started. If I increase the degree of the inner nodes, what does that mean? What does that mean for my inner nodes? Degree is now 4. What does that tell us? Yeah. 3 keys and 4 children. So 4 children being the same as the degree number, right? The degree number tells me the maximum number of children that an inner node can have. In this case, 4. What about the minimum? It'd be 4 over 2, which is 2. So it has to have at least 2 children, can have up to 4, right? That's what that says. What about the leaf node degree? So if the leaf node degree is 3, what does that mean? That's the number of key value pairs that a leaf node can contain. That's the maximum number. What about the minimum number? Is it 1 or is it 2? It's 2. It has to be at least 50%, 50% or greater. 50% or greater. So the leaf nodes are either going to have 2 or 3 values in them. That's it. Reconstruct this tree with these new degrees, and I'll give you a few minutes to do this, and we'll try and sketch this up before you leave here today. I'll be around if you have any questions.
Yes. Yes.
Now we have a push to occur. Let's see, you have merge. And the parent no longer has to serve. Yeah, so we have
Two spaces.
and we'll try to steal a value. And if that fails, so then we remove an entire time.
No. What is the new set? It is 2.3
The largest value in a node is or is made with 110 and then if you merge nodes, then yes. At 4 seconds. Which could trigger something that Deletion is definitely scarier than a lot more potential dangers. The degree of an internode is the number of sets. Or has to have any sort of 2. Yeah. This splits, right? So we're so they get to 2 to 4 to 7 like and this parent gets 4 7. Yeah. So it becomes
Much more.
Okay, let's have a chat about this. We're running out of time. I'd like to at least get part of the way through this problem before you all have to leave. For the first part of this problem, it's actually kind of boring. There's not a whole lot interesting happens. When does something interesting start to happen? At 7? Yeah, at 7. So for the first three values, 9, 4, and 12, what's our tree look like? It's just a node, right? It's just a, what kind of node? It's a leaf node with 9, 4, and 12 in it, right? So up until that point, it's pretty straightforward. When I insert the 7, that's when things start to get a little bit more interesting, okay? So I insert this 7, it's going to go in this node because that's the only node that I got. But this node is full. This node is full up. So what's going to happen? I'm going to split. I'm going to have two nodes now. What's going to go in this node on the left? 4 and 7. And then what goes in this node on the right? 9 and 12. Okay? What happens now? I need a search key. I need a search key. And so this is where we actually kind of have a question to ask, right? There's two values here that you could potentially argue to be a search key. Well, maybe not, actually. I heard somebody say 7 is the better choice. Why is 7 the better choice? Why not 9? 7 is the largest value in the subtree to the left, right? So that makes it a better candidate for a search key than the 9. So 7 is going to be my search key. And I'll hook these up as children. Have I satisfied all the conditions for as far as degrees go and everything? Yep. My one and only inner node, the root, has 2 children. That's the minimum amount that it can have. Actually, though, it's worth remembering that the one node that is allowed to break the rules is the root. The root is the one node that is not held to the minimums that all the other nodes are required. And actually, we would have seen that had I gone through the leaf node step by step. With a leaf node with one value does not satisfy the conditions, but we allow that in the case of the root. But the other nodes also meet the conditions, so they each have at least 2 values, which is the minimum that they need to survive. So we've inserted the 7. So next is the 2. And which insertion case does the 2 hit? The simplest one, right? Nothing complicated. 2, 4, 7. I'm going to insert the 6. What am I going to do with the 6? I'm going to split this node. So this node's got to split into 2 more nodes. Oh, I made that really small. So 2 and 4, and then 6 and 7. And then what happens? The 4 is going to go up the tree, right? So now I have a 4 and a 7. Hook these children up. Sure. And everybody's happy, right? All my leaf nodes have at least 2 values. My root, which is my only inner node, has 3 children. That's okay. Everybody's happy, right? Everybody's good to go. The 1. What happens with the 1? Simple case, right? That's the simple case. Nothing crazy going on there. Let me see if I can make this node a little more roomy. 1, 2, 4. 3 comes along. And that's going to force us to split this node again. So I'm running out of space over here. I've got 1, 2, 3, and 4. Why am I not erasing? There we go. Erasing kind of. Whoop, whoop. Hey, maybe I'll here. I know they watch my YouTube videos. Bill Gates is a huge fan of mine. Not really. 1, 2, and then 4. And then we redraw our children. Sorry, it's crammed in there. Much right. And it's kind of working. There we go. Oh, what step did I skip? Push the 2 up the tree to the parent. So we'll have 2, 4, and 7. And pick up children. Like so. And we're left with 10, which goes on this rightmost node. And so you'll notice that actually this example is less exciting perhaps than the original one that we did. Consider that because the degrees are larger, it takes a little bit longer for exciting things to happen like insertions because they can hold more stuff, right? They can store more things. And that's generally true. As I use larger degrees, right, there's a lot more flexibility there in terms of how many insertions I can perform before I need to worry about splitting, or how many deletions I can do before I have to worry about merging nodes together. So, you know, we see those things happen somewhat frequently with these smaller degree values, and that's good when we're trying to learn the algorithm. But in practice, we really want to avoid those cases because they do take longer, they're more complex, and fortunately, larger degrees will allow us to do that. So, if you have some time, we don't have time to do it today, but if you have some time, you could run through a deletion example on this guy as well. And if you want to chat about that, I got my regular office hours tomorrow morning at 10 o'clock, so come on by and see me. Otherwise, have a good one. I'll see you all on Wednesday.